begin the class. I think the class is half full, but I hope others will join as we go along. So today I want us to discuss a new topic. Like I said, our discussion today is going to delve deeper into how we can manipulate data in PLCs. We have been talking about providing instructions in PLCs through timers and also through counters. However, today I want us to move on to other techniques of providing instructions to the PLC. And specifically, we'll be talking about how to transfer data and also how to do data comparison. So those are some of the techniques that we'll be learning from today in this topic. So I'll share my screen briefly. All right, so our discussion is on data manipulation instructions. So like I've mentioned, we have so far discussed timers. We have also discussed counters as instructions used in PLC programming. Now, if you have noticed, when we mentioned timers and when we talked about counters as well, something was very clear about these two types of instructions. These are internal instructions. And the key thing, if you must have noticed, is that these instructions can only handle a single bit of data. Okay? Meaning that they can only, at their input, they can only take a single bit, which is either a 0 or a 1. Okay? And even their output can only provide a single bit of instruction, which is either a logic high or a logic low, meaning the done bit can either be just a logic high or a logic low, 0 or a 1. So this already is a limitation, because it then means that these instructions can only provide a single bit of data at any given time. But in PLC programs, sometimes we need to involve blocks of data or even blocks of operations. So you want to do a couple of things at the same time, not just giving a single instruction at a time. So if you want to provide blocks of data operations, then we need to look for other types of instructions that would allow us to achieve that. Okay, so this is where data manipulation instructions come in. So here, this is the solution to handling blocks of data operations. So these are instructions that change the content. Change the content of data or the register. And we know that the register is basically the memory. Registers are just memory locations, okay? But the key thing is that data manipulation instructions will perform operations on data and they will also provide computational capabilities. So let me just say, and provide computational capabilities. Okay, so these are the types of data that have, instructions that are very, very important to computer systems, not just PLCs, but computer systems as well. Now, data manipulations instructions are like allowing the PLCs to take up additional characteristics that are just beyond the relay characteristics of just taking a single bit of instruction. This is now allowing us to have more features in our PLCs. Okay, so that's a very, very important point. Okay, sorry, just a minute. Anyway, okay, so let's go on. So now, when we talk about data manipulation, we want to manipulate or even store data that is either comprising of a single word or a group of words, and we want to manipulate this data or even move them from one memory of the PLC to another memory of the PLC. So we look at the different techniques in which we can manipulate lots of information. We know that from our digital electronics, we said that when we have a binary digit, which is the basic building block of any data. So this is the smallest data. We call it a bit or a binary digit. However, we also have words or a word, which is a group of bits. So already you see that we can manipulate groups of data. Because now in data manipulation instructions, we are not just using bits, but we are using words, or other books will call them multi-word, because basically words, let me just say groups, okay? And we want to manipulate this. Now, there are only two categories of data manipulation. So if you have data manipulation instructions, then we can categorize them into two main areas. The first area is we can do a data transfer. That is one way of manipulating this data that we are talking about. We can do a data transfer, which basically involves location, changing the location of data. Or we can do data comparison. So within data transfer, there are several things, but the key thing is we change the location or the memory location of data within the PLC. Now remember, the PLCs are also just computer systems. So they operate basically on the architecture of a computer system. So data transfer is just how to manipulate or change the location of that data. But we are actually changing groups of data at the same time. And data comparison, we'll look at it in the second segment of our discussion, which then will allow us to understand that now the data comparison has a lot to do with logical operations, with math functions. This is where we do data conversions. We do logical operations. So this only affects change of location. But here, we would want to do a lot more. We would want to do logical operations. Let me just say logical operations with that data. So once we are able to understand some of these techniques, then data manipulation instructions would be a done deal for us, okay? Now, because we are doing manipulation of data through these PLC instructions, there is a key thing that involves data manipulation. Because the manipulation, when we say we are manipulating, there's got to be a location in which we do the manipulation. That location is registers or memory locations. So if you're doing a data transfer, you have to transfer from a source and do it to a destination. You're simply changing the location. The location is not physical, it's memory. It's register based, okay? even data comparison is done within the memory itself. So data manipulation instructions need to have what we call a source address and a destination address. So, and especially when we are doing data transfer, we'll have to specify the source of the address and the destination address from where we achieve the manipulation, okay? Now, overally, data manipulations are performed internally. I've told you this is like a computer system, and so these operations are performed internally in a manner similar to what we do in microcomputers. I think by now, especially in fourth year, you must have done things like the 8081 or 8085 microprocessor and stuff like that. So because you have 100 microprocessors, data manipulation works in a similar manner in the way we do microprocessors and how we even do the addressing and so on and so forth. So that's a very, very key thing to remember as we move on. So please remember, we have data manipulation, which is the instructions that operate on groups of data or a word data. And it's different from the single bit instructions that we dealt with timers and also with counters. Now, two other things to remember before we continue the main issue is that we have classes of instructions. I have just mentioned that because this manipulation happens in memory, it happens in registers, okay? And it affects a block of data. These instructions that operate on data or on groups of data, they can operate on two classes of instructions. One, they can operate on what I've just said, on word data, or they can operate on a file data. Okay, so these are just two types of data instructions that we are working with. Okay, so what is our word data and what is file data? I will share notes. I'm still compiling and a few notes that I will share with the class rep. But what we must understand is just typically, if we were to take a memory, let's just say this is just a section of the memory. Okay, let me just say section of memory. Okay, and in computer systems, memories are partitioned. Okay, so let's say in this memory we have segments like this. Now, each of these segments is known as a register. It's a portion of the entire memory. It's a sub memory, for lack of a better word. So this is known as a register. Other books will refer to this as a word. And if you look at it, basically what it is it's a segment like that, which again is comprised of bits. I told you we are now working or manipulating groups of bits, not just a single bit. So you might find something like this. So this is a typical example. So if I plucked out the register, then it translates to this. This is how it looks like. Okay. Each register contains binary digits, or what we are calling bits. Okay. So that is a word. So every time now, when we refer to a word, we are not talking about our text words. We are talking about a group of bits that we are calling a word. I think actually, if I remember correctly, digital electronics, a group of 8 bits is what we refer to as a word. I think so. You can check that. Now, remember, I have said that we'll be manipulating a word or a file. Whenever we are doing data manipulation, whether we are moving or storing or whatever it is we are doing, or even logical operations, they'll either be done on a word data or on a file data. So what is a file then? Because we already know what a word or a register is. So every time you see a word or you see a register, it means the same thing. It's only that now different authors or books will refer to them in that manner. So a file itself is a group of registers, okay? If you have a group of registers. So for example, if we take up this section here, let's say you have this section here. Just trying to, let me just take 4 of them like that. So this guy here is what we refer to as a file. In fact, other books will call this a table, okay? It's a file or a table. Basically, it's a group of registers combined together. And each one of them, of course, as you now know, will contain bits, okay? Each one of them would contain bits. So this is how we differentiate between a file and a register. So if you have a group of registers, then that is referred to as a file. Other books will call it a table. So again, if you meet references to, or if you meet these words, then it should not be confusing. Now, the other thing that I need to mention, just to avoid confusion at this point, is that we have said that a file or a table is a group of registers, but they have to be consecutive. So let me just say a file, or what we are referring to, a table, is a group of consecutive. They have to follow each other. You see, like I have illustrated there, a group of consecutive words, okay? A group of consecutive words, or what we are calling registers. So if they're not consecutive, then they're not called tables. So if one is here and then there's nothing there, and then another one is here, then we cannot group that and call it a file. They have to follow each other. Okay, they have to follow each other. Now, again, different PLC manufacturers will have their own set of data manipulation instructions. So what we are going to discuss today is not the entire set of data manipulation instructions that you may encounter in the industry. What happens is we are going to discuss the basic data manipulation instructions that you may encounter, but others may not be available for us now because either they are not covered by the type of PLC. If you've noticed, our PLCs has just been, we keep referring to Siemens and maybe the Allen Bradley, the Rockwell PLC. But there, like we had mentioned earlier, there are several, but we don't have enough time to look at each one of them, okay? So even the format of these instructions can vary from one manufacturer to another. The thing that you have to remember is that the concept of data manipulation will remain the same across all manufacturers. They may use a different format. They may use a different set of instructions. So there are instructions that you might find in Rockwell that you will not find in Siemens. But basically, the concept of how you manipulate data, whether it's through data transfer or even through comparison, data comparison, the concept remains the same. So whichever instructions you learn, then you still will be able to understand the whole thing. That's why it's always important as an engineer, especially if you're dealing with a specific industry, then you understand what manufacturer they prefer. You look for data sheets, because within the data sheets, there's a lot of definitions of the instructions that are specific to that manufacturer, and then you can quickly adapt to it. Okay, so remember, we have data manipulation instructions. We have categorized this into either data transfer, which involve transferring blocks of data from one location of memory to another, or data comparison, which involve logical operations or math functions, as we shall see in a short while. So let's start with the first one, data transfer. Okay, data transfer. I'll try and move quickly on this because most of it is theoretical, but in the subsequent class, we'll probably look at some of the practical applications, because I just don't want to give you abstract information. I'd like you to see how you can apply them in real life. So in data transfer, we have several commands here that we use. So let me say there are several commands used for data transfer. So we'll quickly look at some of these commands, and if time allows, we'll move on to the other logical operations. The first one, that's one of the most common data transfer commands, is the word move. Now remember, we use uppercase abbreviations to denote these commands. We don't use the lowercase because we intend to separate it from our usual textual or communication that we do. These are computer commands, so they must be different from our type of communication, which is human. Okay, so when we move stuff like this is human language, and so it's based on decimal number systems. But when we move MOV, then this is based on bits, binary digits, and it's computer language. But the thing here is we understand that that command can move the source file. I told you you must have a source file, so it moves a source value or a source data, let me just say source data, to destination. Moving involves a source data being taken from one memory location to another, or from one register to another. And you're not moving just a single bit, you're moving blocks of bits, you're moving a word. Sometimes you're moving an entire table or an entire file. And it's easy to relate to this because we do this, especially if you've interacted with your computers and you're doing things like when you're in Word document, you can move a section or a block of texts and move them to or even a file. You can also move a file from one source to a destination. Okay. The other type, this is now a type of move which is very, very critical and is used a lot, is abbreviated MVM. This is a type of data transfer that really only happens in computer systems, and it is referred to as a masked move. We'll see what it is and what it is all about. Okay. But in a nutshell, masked move is a way of moving data still. So I'll say moves data from a source location, but with a twist to a selected portion of the destination. So I'll explain this further. But masked move is a very controlled type of move. Whereas in move, we take the entire data that is in the source destination, in the source file or the source register, and move it to that entire data is moved to a destination of the memory. But in masked move, you're moving data, but only to a selected portion of the destination. I'll give you an example in a short while. The other commands, and these ones, of course, now I am sure you have met before, are the logic functions that you've met before, and these ones should not be difficult now. This one is like the bitwise AND operation or AND function. Let me just say AND operation. These ones you did in third year, and you did a lot of truth tables and all that. So this is an OR operation, again, which is just a bitwise OR operation. There's nothing new. In fact, these ones I'll not even be bothered with as much as the first two types of instructions. You know that we also have the XOR, or what we refer to as humans as exclusive OR. Okay, exclusive OR, where we actually performing bitwise XOR operation. These ones I won't bother with. And then, of course, NOT function, which is, of course, a bitwise NOT operation, which is a negation, or we call it a negation, we call it a complement, we also call it, I don't know, I've forgotten some of the terminologies used. We also have the clear, okay? What we refer to as humans as clear, which is having, let me just say, setting all bits of a word to 0. Okay? Now, there are other commands, several of them. There are several other commands. I cannot just be able to discuss all of them here today, but there are several. Okay, sorry about that. So now I want us to look at the first two, because those ones you might have maybe just heard about them, but you haven't interacted or even seen how we achieve the manipulation of data using these two types of commands, the move and the masked move. Like I said, the rest, I'll try and include them in your notes, but I'm not really worried about them, because by now, because you did them from third year, and you even have a lab component that involves the logic gates or the logic functions. And so I'm not worried, won't test you on your understanding of those functions. So let me start with the move instruction or the move command. Remember, we said that command is in uppercase, not lowercase. Now, this is a very simple command, which I've said simply involves the transfer of instructions, transfer, let me just say transfer of contents, let me use a different term, from one word. Remember, I said if I say word now, you should also know I'm simply referring to a register, to another. But I would caution that you take it seriously. It's very, I have said this before, and only half the class is able to demonstrate that they understand the move command and how it's implemented in PLCs, because we take it so casually just from the word move, so we feel we already know what it involves. But when you actually look at how that implementation is done in PLCs or on moving binary data or a block of data, you notice that there are certain very subtle information that you can easily miss out on, and when you do, the whole thing is wrong. The move command is not, you're not able to provide a proper interpretation of what it is all about. The definition is very straightforward. It simply sounds like you're taking the contents of information or data from one register and you're moving them to another register. Remember, we are calling, we have a source address in this case, and you must have a destination address, which is another memory location. Now, let me show you how this probably is in the memory location. So let's say we are taking a word, okay? So by now we know that we have a word, which is a register that has certain bits. Let me use 8 bits, 1, 2, 3, 4. So 8 bits, okay? There could be, of course, 8 bits is a very small set of register. In fact, these days it's very difficult to find an 8-bit machine. Even phones are not 8 bits. Even your calculators might be more than 8 bits these days because of the computations that they're capable of doing. So I think the smallest that you can have is a 16-bit machine, and the memory is 16-bit wide. That's what I'm saying. But for purposes of illustration, let me use an 8-bit. It's generally understood that a word is a group of 8 bits, but because of advancements in technology, I think it's very rare to find an 8-bit machine today. Those ones are very slow, and they probably are limited in their capacity. So maybe the smallest you can find is a 16-bit. I'm not even sure that the smartwatches are 8-bit wide. The memory is 8-bit wide. They're probably more, okay? So anyway, the idea is here. So let's say we have an original data. So somebody has a data in their source location that looks like this. Okay, maybe I need to be smart. So let me use a different marker. So each register is always, because it's an address, it must be addressed. It must have an addressing type. So let's say we are calling this N710. Okay, number 7, part 10. That's a portion of the register. Okay, now let's say we have another register. This is where I say students always tend to take this casually and make a very simple but very costly mistake. So let's say we have another set, and this one, let me just assign arbitrary bits here, like that. And let's call this also maybe N7. They're in the same block, but let's say 20. Okay? So you have information that is in register N710 and another information that is in register N720. They're different types of information. So if you are asked to perform a move operation, you have to know what the source is, or what the source address is, and you have to know what the destination address is. Now, in typical computer terms, to perform a move operation, so let's say we want to move, and just say we are typical, so if I want to perform a move operation, then now I will have a PLC. So let me use that. Okay, let me just quickly draw. We want to perform. Remember, this move is also an instruction, just like timers and counters. So we represent them using a block, but we have to specify what this block does. So this is a move operation. And I told you, usually you have to write, just like when you write an timer on delay timer, you have to write inside there that it's an on delay timer. So the instruction here is to perform a move operation. I've told you that the key things that are required when you're performing a move operation is a source and a destination. So this must always exist. So let's say in our case, the source is N, let me say this is the source and this is the destination. So what I mean is this address is our source address and this is our destination address. So our source address in this case is N720, N720. And our destination address is N710. Okay? So then we can perform a move operation. So you know the section. So let's say this is sort of like your input. So you've got a switch here that if closed, then it activates the move instruction. So what happens is, because we have a set, you have your register there. Okay, you have your register, which I'm just writing a portion of it. So let's say this part here, this section here, this is just a portion of the register because I can't draw the whole thing to scale. Okay, so let's say that this address here was, this is your N710, N710, and this is your N720. So when we execute the move instruction, the idea in PLCs is to take the contents that are in the source destination and put them in the destination address. So it's like, but in the destination address, there was already information there. So like you can see that in our destination here, we already have some information in it. But because we are moving information from the source to the destination, we are writing over the existing data. So the process, let me just say that the process involves writing over the existing data in the destination address. Okay, so therefore it means we'll take the contents of N720, we'll take the contents of N720, these ones here, and move them to N710. So let me put that arrow there. So we take the contents of N720 and move them to N710. What that therefore means is that the information that was in N710, the information that was originally in the destination address, is written over. Okay? Now, this is where I said students make mistakes. When we perform a move operation, it does not mean that now that I have moved the contents of N720 to N710, that now nothing exists in N720. We retain the information that was in N720. So a move operation can be compared to copy pasting in Word, for example, in Microsoft Word. When you copy paste, the source address retains the data that was originally there. It is only the destination address that is written over. So over the years, I've seen students thinking that because you're moving, you think of like when I'm moving from one house to another. So it means that the content that was in your previous house now is transferred, and so there's nothing left behind. In move operation, especially in data manipulation instructions, the source contents are retained. It is the destination address that is written over. So therefore, what will happen? This was before the move operation. So after the move operation, let me now draw. After the move operation, the destination will be like this. The destination address. This is after the move operation. I think those are 8. So the content would be what was in the source destination, which is 1, 1, 0, 0, 1, 0, 0, 0. So you see that whatever was here has now changed. Okay? But whatever we had in the source destination remains the same. Nothing changes there. So move operation is like a copy paste. So what we have here, we're still going to have this. So essentially, we've duplicated the contents of this source to the destination. So our contents now for the source is the same as the contents for the destination. So the source doesn't remain with nothing. Okay, that is what I wanted to emphasize for you. But I've also at this point indicated to you how that is achieved using a logic, a ladder diagram, okay, where we are using the move instruction to take, so that when you when now the switch, when somebody makes the switch, then of course the move instruction is activated, and then whatever was in the memory location is affected accordingly. Okay. So the source value remains unchanged. So we say that there's no data conversion in the move instructions in the source. So here there's no data conversion. Okay, but the information that was in the destination is written over. Okay, sorry about the noise. Now, the other thing that maybe I mentioned as I finish this portion of the move, then we move on to the must move, is that the instruction, the move instruction or the move command may have certain input conditions. When you're programming it, you might have certain input conditions that precede it, or you may just program it unconditionally. This is what I mean. When we are drawing the ladder diagram, you might find, because I want this to be as practical as possible, in the real world, you might find that before this move instruction is executed, you must probably have certain input conditions indicated here, okay, that must be met before the move instruction happens. Alternatively, it can just be programmed unconditionally, meaning in this case, no initial conditions are set. Okay, so it's just activate the move and execute. But in other cases, which is what is most common in the industry, you will find that there's a set of instructions that must occur first. or a set of instructions that must be executed fast before the move operation. So when you're programming or when you're coming up with your ladder diagram, you might find that you need to have a certain input conditions that must precede the move command. But otherwise, you can also just use the move command as is. You see, just like we were doing with timers, you want a certain condition to be met before you bring in the timer or before you bring in the counter. But for move operation, you can just use it without any preceding conditions. So it's just like I switch on or I activate my move command, and the move happens without any preceding conditions involved. So that's why I'm saying it can be executed unconditionally. You don't need previous conditions for it to work, but you can also work with it when you have certain input conditions to precede it. So I hope that is clear. That's important. Now, this is one of the most common commands that we have in PLCs. I will not make any other comment beyond that. That should be enough. So let me move on to the other one, which is also very, very critical. And this is the masked move. Again, here, there is always tendency to make rookie mistakes where you take them to be very simple instructions and then you just miss out on one step and then it makes the whole thing wrong. So over the years, I'm always shocked at how students are overconfident with some of these instructions, but when they are tested, they make mistakes and then they get the whole thing wrong when you expected this to be free marks. Okay. So again, I ask for your indulgence and pay attention on how masked move works. And then I think from there we'll see. So I told you initially when we were starting that this is a very special type of move. It's different, not widely, but it slightly differs from the move instruction that we have just talked about. Okay. Here, the word mask is involved. Masked move. So here it simply means that the data that we are moving, the data being moved must pass through the mask to get to the destination address. Very, very important. That here you're just not moving the contents of the source to the destination straight away. You have to go through a mask. So the mask itself is a control mechanism. So what is masking? What is masking as used in computer language or PLCs in this case? So masking is just the action of, let me just say, the action of hiding a portion of the binary word before transferring it. And this is why it's a very, very important type of command, transferring it to the destination. This is why it's a very, very important part of the PLC command. And you'll see it helps a lot, especially with maybe can be used in security systems. Okay. So again, the best way for me to illustrate this is to show you examples, maybe with a certain memory location. But what is important here is you have source information, then you have a destination address, but in between the source address and the destination address, there is a mask that is involved. The work of the mask in electrical terms, it's like a filter. So the work of the mask is to filter out certain information before it reaches the address. So move was taking the entire portion of the source information and duplicating that in the address destination. I mean, the destination address. But for mask, that information needs to be filtered first before it is allowed to get to the destination. Now, how do we do the filtering? Because a masked move is a conditional. There are conditions that must be met. So how do you filter that information? So there are two, for the mask, the conditions, it's very simple. The bits in the mask, because the mask is also a memory address. Please remember that. The mask is also a memory address with bits in it. So the bits that exist in that mask, the bits that are set to 0, the bits in the mask that are set to 0 do not pass data. Think about it the way we were looking at high pass filters and low pass filters. Okay. Sorry guys, let me pick up this call. Just a minute, please, as you interpret. I'm sorry about that, guys. I had to take that. So let me just go back to our discussion. My apologies. So we were talking about the masked move, and we're looking at the condition of the mask, because remember, we are looking at what must be done before information is moved to the destination. Sorry. So the bits that are set to 0 will not be passed. I'll give you an illustration, so don't worry. The other conditions is that only, let me say, only the bits in the mask that are set to 1, will pass data not just data, will pass the source data, will pass the source data through to the destination. So these two conditions are very important. I was saying, let's think about it like filters. There's a condition for filters, and in filters, we use frequency. So for a low pass filter, for example, certain frequencies below a certain fundamental frequency are allowed to pass, while anything higher than that is not allowed to pass. Okay? So the same way here, if the mask has a bit set to 0, then it means that the corresponding bit from the source destination is not allowed to pass. But if the mask has a bit set to 1, then the corresponding bit from the source destination is allowed to pass through to the destination address. I am going to illustrate that a little in a little while. So basically what we are saying here, that those bits that are already in the destination are not affected if the corresponding bit in the mask is 0. Because remember, again, in fact, the best way to illustrate this is to draw, let me just show you again. And now, again, typically we have 16 bits and above, but let me use 8 bits for illustration purposes. So let's say this is our source bit. Let me call it source. It can be any number. Let's call it A. A30. Okay? Let's give it some numbers in here. Something like that. Then, remember, we have a destination. That destination also has some information in it. We must never forget the destination is always not just that it's empty. It also has some information. So let's say the information there is at the destination at any given time was this. Something like that. That's the destination information. Okay? So let me call this destination. Remember, we are looking at how to implement a masked move. A masked move. So let me call this A37. It's just an arbitrary addressing. But now we have a mask. I'll draw the mask. So the mask, one condition is that the mask must be of the same bit size. The length of the mask must be of the same bit size as the source and the destination. They must be of the same, because you know you can't do this masked move if the lengths of each of these registers are different. They must be the same. So if one is 8 bits, the others must also be 8 bits. If they're 16 bits, all of them must be 16 bits. Otherwise, you will not achieve the desired instruction as expected. So let's say in the masked move, we have this kind of just an arbitrary stuff. I'm just giving, yes, arbitrarily. I hope those are 8 bits. Okay. So again, this is a mask. Now the mask typically is not addressed I mean, the not address. It's addressed. Actually, let's give it an address so that we understand what I'm trying to say. Let's call this A31, maybe A31. But the mask is usually in hexadecimal number. So there's usually a hexadecimal equivalent. So these bits here have a hexadecimal equivalent. I don't know what the hexadecimal equivalent of this is. I would need to do that conversion, but the mask needs to have a hexadecimal equivalent. I think we can do that. Maybe a lot of us have forgotten. If I want to do hexadecimal from binary, it's usually easy. I divide them into groups of 4. 1111 is 15. 15 in hexadecimal, I think, is F. 0010, I think, is 2. Something like that. So it means that the mask usually is given this address, not address, is given is written in hexadecimal format. So what I was saying is you might find that either some PLCs provide an address for the mask, or some PLCs will provide the hexadecimal format, or just displays the value in hexadecimal format. That's what I was trying to say. So if you find PLCs that provide an address for the mask, just know it's fine. Others might not have the address, but they have a display of the mask in hexadecimal form. Again, no, that is just a standard way of displaying the mask. So you should not be scared about it, because they say one and the same thing. Just like I told you, different manufacturers prefer their own different formats. Okay, good. So let's continue. Now let's understand how we can actually perform a proper masked move using this kind of example. Remember, the conditions were, you look at the digits or the bits in the mask. For bits that are 1, then the corresponding source bit can be allowed to go to the destination. But for bits that are 0 in the mask, they block. That's the word. They either block the source bits from reaching the destination. So what happens is, in that case, the destination retains the information that was in that corresponding bit. Let's see for an example. So what will happen is, what will finally, when we perform a masked move, this is what we'll have. So let's say we've performed a masked move. We'll still have 8 bits. Hope those are 8 bits. Let's see what happens. If you look at the source here, we have a 1. The corresponding mask is a 1. So that means that it means allow whatever is at the source to move to the destination. So the destination would be 1. Why? Because we wanted to transfer 1, but through the mask. The mask is providing a 1, and that allows us to transfer that information to the destination. So the destination would be a 1. Okay? So here, the destination already had a 1, but at least we know that if it was a 0, we would have changed it into a 1. We would have overwritten it. Okay? Let's go to the second one. You have a 0 here, and you have a 1, meaning you're allowed to transfer that 0. The 1 in the mask allows the bit to be moved to the destination. So you see the destination here already had a 1, but we are now transferring the 0. So we'll overwrite this 1 with a 0. Hope that makes sense. I'll repeat. Notice that all we are trying to do here, the determinant of whether we do a move or not is determined by the mask. If the mask has a 1, then it allows us to do the move, just like we were doing move previously. But if the mask has a 0, it's going to block us from doing the move. That's basically what a masked move is. So here we are allowed to do the move, and so we can move this 1. Here we are allowed to move the 0. So you can see we are transferring this to 0. It's now moved to 0. Okay. And we do that for each one of them. Here we have a 1. A 1 allows us to move the 1. So it means we'll have to move the 1. We have a 1 here. It allows us to move the 1. Okay. Here we have a 0 and we have a 0. So notice, because we have a 0 in the mask, it blocks us from moving. So the thing is, once you see a 0, it means whatever was at the destination is retained. Whatever was at the destination is retained. Okay, that's very critical to remember. So whenever, because like in this case, I'm referring to this case here, you see here we have a 0. The mask is a 0. The mask with a 0 means block that move instruction. So it means that 0 is not moved to the destination. So whatever was existing at the destination at that point, which is this bit here, is what we'll still have. So it means we are not overwriting or we are not replacing that bit. It remains the same. Let's go on to the next one. We have a 1 here and we have a 0. So a 0 already means we are not moving anything. So whatever was at the destination is retained. 0, 1. So that allows us to do the transfer. So here, 0. 1, 0. That means we block the 1. So whatever was at the destination is what is retained. So therefore, this is the destination. This is your destination, A37, after masked move, after our MVM, okay? After the masked move. So basically, the masked move is like a filter for those bits that are designated 1 in the mask. They allow for the move operation to happen. But for those bits that are designated 0 in the mask, they block the move operation. So we only retain the information that was originally in the destination that corresponds to that bit. Okay? So where there is a 1 in the mask, data will pass from the source to the destination. Where there is a 0 in the mask, data in the destination is retained, or it will remain as it were in the last state. Okay? So the mask must be the same size for this to happen. You'll notice that the mask must be the same size. The register must be the same as the source and the destination. So you can't have an 8-bit source with a 10-bit mask with a 16-bit destination. They must be of the same bit. So how do we implement this again in PLCs? Again, it's very, very simple illustration, just like we do with the others, where you have your ladder diagram like this. So let me call this switch A. So that is A. Okay. So this is a block for the move. So this is how the move operation works. Again, remember, you have to write MVM and you have to state what that is. Masked move. Okay? There are 3 things. We must have a source, we must have a mask, and we must have a destination. These ones you will have to know by yourself. Every time, just like when you're putting a timer, you know what elements that constitute that timer that you must indicate. You must indicate the done bit, you must indicate the preset, you must indicate the accumulator, and so on. So here, for example, our source was what was our source? A30. So source is A30. The mask is A31. So this is A31. A31. This is where I said in some manufacturers, they'll write A31. Other manufacturers will simply write F2. The hexadecimal format, F. It was F2, yes, like that. And then, of course, the destination address, which is A37. Okay? So that is how and actually you might see, I think in some books you will see, or in some PLCs, you'll see that they don't just write the source here, they'll also write the bits that correspond, or the bits that are stored in that source. Like in our case here, the bits were, I think, 1011, 0101, like that. And then the destination is now what, after the mask, before the mask happens, we had a 11011001. Okay, this is before the mask happens. So after the mask happens, that's what the output will show. After the mask move has been executed, that's when you will see what happens. Okay. Now, I told you that there are other commands that exist within certain manufacturers, but are not there in other manufacturers. I will give examples in the notes. I'll not discuss them here because it's not good for us to discuss what's specific to one manufacturer. It limits our thinking. So what I'll do is I'll just give examples to illustrate some of the commands that may be included by certain manufacturers, but they're not necessarily universal. So they are not as important. You're only supposed to know them when you're using the PLC from that manufacturer. But the ones we are discussing here are sort of universal commands that are understood across all manufacturers. Okay. So again, because today I'm doing a lot of theory, in the next class, we will do examples that now include, for example, we look for a typical practical example like we've been doing before, where you can now include maybe a timer. You then need maybe a counter, you need a move, and you need a must move. So it's an application that involves incorporating some of this. So you know that not only do you always use timers and combine timers and counters, but we can also combine them with these data manipulation instructions. So we can also combine timers with move instructions and with must move instructions and so on. So we look at examples later, practical examples, and try and solve them when we meet. So today I'm just trying to cover the different types of data manipulations that we have. Okay, so that we'll do the real work in the next class. Now, there are also types of move instructions. This is also, I'll mention it, most of it I'll provide you in the notes. So types of move instructions. Remember, ladies and gentlemen, this is what I'm trying to say. We had said that you can have just a register like that, or you can have a file. Okay, so you can have a file, a group of consecutive words or registers, a file like that. So typically, there are things that you can do. One, you can do what is called a word to file move. A word to file move, where you have a word like that. So this is your word. And then you move it to a file, a table like that. So you have a table like that. So this is your file or table. So this means that this word has to be moved on each corresponding word in the file. So you are basically transferring. I need to put an arrow here to show that this is what in communication systems we call broadcasting. You're copying a register or information within one single register, but it is copied to a table. So it's copied to several different registers. So this is, for example, when I'm writing an email to an address that has 20 people. So I'm just giving that analogy so you think of a word to file move is like that. You have a single instruction, which is a move instruction, but you're moving a single word to a whole table, okay, or a whole file. So that means, and it's a very practical way of move that we do. So our moves are not just limited to word. It can also move from word to file. We even have a file to file move. Okay, a file to file move. This is like now you're trying to move large amounts of data and you're passing them on at the same time. Okay, so like you have this, so you have a file there like that. Okay, and then you have another file there like that. You have another file here like that, right? So you have file A, this is file B. So I am transferring the contents of file A to file B. How does that happen? Very easy. This is moved there, this is moved there, this is moved there, there, and there. Just like that. So this is a file to file move. A file to file move. We can also have a file to word move. Okay. So the other type is a file to word move. A file to word move. So you have a table, which is a file. I'm using those words interchangeably so that you don't forget. And then you have a register, which is a word. Okay. So you have your file there and you have your word there. And so a file to word simply means each of these information is transferred here. Like that. Each one of them is transferred there. Okay. So more of like, think of like your inbox, your inbox, your phone inbox, or even your email inbox. It's just one inbox, belongs to you, but receives information from several files. Okay, so people can send you, maybe your inbox is a pay bill number. So several people are depositing into your pay bill. Okay, that's a file to word move. A table to register move. Okay. So most PLCs, ladies and gentlemen, most PLC manufacturers will display the file instructions in the block format on your terminal, on the screen. When you're using Simulink, for example, or when you're using the software, you will see that they use just the block diagrams to sort of display the instructions that are being executed or the instructions that need to be executed. So basically, this is information that's critical for you to know. Again, I will provide sets of instructions, sets of questions that we can solve in the next class that make use of all this. Okay, I want to conclude because I have a CAT to administer, but allow me to move to the second type of data manipulations. If you remember, it was data transfer and data comparison. So let me move to data comparison. Again, one which is not very unique or unfamiliar to you guys, because data transfer operations are all output instructions. So data compare instructions are input instructions. I'll repeat that. We have done data transfer. These are output instructions. If you have noticed, if you are keen enough, let me take you back. If you are keen enough, let me take you back. Look at that ladder diagram. It is not connected to any output. Typical ladder diagrams, we usually have the output connected. Here, it's not connected. Why? Because this is already an output instruction. I remember even the move instruction. If you look at the diagram that we drew, this is an output instruction. Because it's that instruction that affects the memory instantly. It's already an output instruction that's going to affect what happens in the memory address. Okay? It's going to affect the registers in the memory. So it's not an input instruction. So data manipulation, in data manipulation, we have data transfer. Data transfer are output instructions. But now, data comparison instructions, you will see, are input instructions. Meaning, if you're drawing ladder diagrams, we'll still have to have outputs. Okay? So these guys can affect the output field devices immediately. Okay? So data compare instructions are used basically to compare numerical values. Compare numerical values. This is not unique or unfamiliar to you guys. You've done this ever since kindergarten. But what we are doing now is we are comparing data stored in 2 or more registers, and we are making decisions based on the program instructions. So there's a program instruction that exists, but we are comparing data that exists between 2 registers. So these numerical values exist in 2 different registers, meaning 2 different memory locations. So we can compare those for each of the basic instructions that we have based on the PLC. We have used comparisons before, certain data comparison concepts, when we were dealing with timers and counters. Okay? But here we have input instructions. If you remember, for when we had the timers and the counters, there were certain conditions that maybe an output was turned on or off when the accumulated value of the timer or of the counter equaled the preset value. So you see, you already used a data comparison there, because you're saying output will be turned on or off when you have accumulated value equal to, or even with the done bit will go to logic 1 when the accumulated value equals the preset value. Meaning we had to compare the accumulated value and the preset value. Now, in that case, the accumulated numeric data, whatever was within the accumulated value in one memory, was compared to a preset value of another memory. Okay? so that when they were compared and they were equal, then the done bit either was logic 1 or logic 0. Okay, so it means therefore that we already tested, we did a comparison of data. So remember, timers and counters already use data comparison instructions. Okay, but of course that one was the equal, because let me give you the comparison symbols that we have. So we have equal to, which we have dealt with. These ones, you know, there's nothing not equal to. So these ones are not very unique. I'll not spend a lot of time in them. Less than, we know that as well. Greater than, that one is known as well. Less than or equal to, less than or equal to, we know. We also have greater than or equal to. This we know as well. So these are instructions that are not new to you. The ones that the way we write them in PLC, these are just symbols that we use, okay? But in PLCs, we don't use symbols. We know, just like we did with data manipulation instructions, we use certain abbreviations, okay? So we don't have these symbols. These are mathematical symbols that we understand as humans, but we can convert these symbols into abbreviations that we then apply in PLCs, okay? So in PLCs, there are more than just, the data comparison is more than just what I have indicated here, okay? So the instructions are so many. There are others that you might have not heard about, but let me start with the first one, this guy here. This is known as the limit test. We've done it in maths as well, but in PLCs, it also exists as LIM, the limit test. So this is usually is to test whether one value is within limits or within range. That's what the word we use, of two other values, It's within range of two other values, okay? We look at examples. This is also very important. These are the ones that I like testing because they're not as common. I mean, we've not met them before. This is known as the masked comparison for equal, like this one, okay? So this one simply tests portions of two values to see whether they are equal. They are called masked comparison for equal. So it means, again, just from the word mask, you have a 16-bit source address, you have another 16-bit information, and then you pass that through a mask. And when you're passing it through a mask, you're checking whether the portions, remember I'm saying portions because the mask will only allow portions of bits to be compared. So it means if you have a 1, then you can do the comparison, whether the source is equal to the destination or the information that you're given. If the mask is a 0, then now you are not allowed to do a comparison. You simply retain what was in the destination. But here you're doing a comparison. You're not moving. You're simply doing a comparison. So this is called masked comparison for equal. It's not masked move. You're simply comparing. So the others that, of course, you now know, the equal one, we usually use this abbreviation for equal. Okay? So this is to test whether two values are equal. Remember, these are data comparison instructions. So you're simply comparing. So the not equal one, we abbreviate it NEQ. Okay? So this is not equal. Again, to compare whether one value is not equal to a second value. Okay? So this one is maybe test whether two values are equal. This is to test whether one value is less, this is not equal, is not equal to a second value. Okay. These are very, very simple stuff. I will do applications that make use of this, and then you'll see how interesting they are. And the same thing is with less. And less, this is, of course, less than. Again, I'm tired of writing. So less than is, again, to test whether one value is less than a second value. I'm just giving you the abbreviations that we use in PLCs. So greater than, we use GRT to refer to as greater than. Now, the reason why you have to know all this, ladies and gentlemen, is I will test you, and you need to know that if you are to draw a ladder diagram, you'll have to draw a block. That block will have to be labeled. So if you are to test whether one value is less than another, then you have to draw a block diagram and abbreviate it as LES, and then write what that is, which is less than, and then put the source address, the destination address, and so on and so forth. That's why you have to know these abbreviations, okay? Then we have less than or equal to. Less than or equal to is just LEQ. So you'll notice we use a 3-letter abbreviation for all this. If you've noticed, all our data manipulation instructions have a 3-letter abbreviation. So LEQ. So don't show up with your 4-letter abbreviation. So LEQ, you can guess that is less than or equal. We have, which other one is remaining? GEQ, greater than or equal. Remember, the function is to test whether one value is greater than or equal to a second value. Okay? So these instructions, ladies and gentlemen, are very important. You have to know how to draw them as a ladder diagram. The operation of the test is known to you because you've done maths from kindergarten. Okay? So, for example, what I mean is, if I was to compare whether two values are equal or not, then you have to just know that all I have to do is draw a ladder diagram. Remember, I said that the data comparison instructions are input instructions. So you don't need a normally open contact or a normally closed contact. You need the input instruction itself. And then you'll need an output. Remember, data, the ones we did previously where we were doing the move, so the data manipulation, where we had the data transfer, those were output instructions. So we were putting them on the output. But here, because data comparison is an input instruction, we must have an output. So that's how you connect them. So for example, if this one was equal, so I'll have to write EQU, then I'll have to indicate this means equal. Then, of course, I'll have the source, okay? Source can be A, okay? Then I'll have whatever is stored in the source is some value. then I'll have another source B. Remember, the reason why I have two sources is I am comparing two values, one from the first source, another one from the second source. So there's no way I'm saying source and destination. This is equal, comparing two values, one from source A, the other one from source B. And so you're comparing them. If they are equal, so what the PLC processor will do is, if the value stored in source A, and remember they are in terms of bits, is equal to the value stored in source B, then if, let's say this was a pilot lamp, the output is activated. And so if you had a lamp out here, the lamp will light up. So this is your pilot lamp, for example. That's what we mean. And equal means this. So if source A, then we have source B. So equal, it means, remember, computers think in binary numbers, but we human beings think in decimal numbers. So let's say, let me use 4 bits. I know, 4 bits. No, even if I use 5, if I have 1 0 1 0 1, 1 0 1 0 1. So these, whatever this is equivalent in its decimal, must be equal to what this is in decimal. So if these two, source A and source B, are equal, then the output is given a logic high and the lamp will light up. Okay? So remember, we know that the computer will be checking the equal. So you have source A being equal to source B in binary. But we humans, it's like saying 34 equals to 34. So if those numbers are equal, then we have our output being activated as required. And that doesn't just have to be equal. It can be not equal. So again, if you have not equal, then you have source A, and then you have source B. Source A, if source A was 30, source B was 25, then since 30 is not equal to 25, the output is activated, and so on and so forth. So you can put all the other commands, greater than, so, but all you have to remember is you're comparing values from two sources. Values from two sources. To do all these tests, you have to compare value from these sources. The only one that's different is the limit, because the limit tests whether values are within limits or within the range of two other values. So I'm going to try again to include in your notes all these instructions and with a typical implementation in PLC, so that you're able to see. I've just told you that the limit one would be a little bit different because you're not comparing two sources. So the limit one would be something like this. For just an example, let me just give an example. Remember, it's also an input instruction. So we will have an output like that. Okay. So, of course, it is LIM, and we say we write that it is limit test. So we are testing. But if you're testing something, we just have to think about it. It's like you have something here. So there's a lower limit and there's a higher limit. So you want the range of between some value. So maybe 10 and 20. So anything that's greater than 10 or, I mean, less than 10 or greater than 20 is off. What is true is what falls within that, okay? So it means you'll have here, you'll have a low, that's why you have to know each one of these. You'll have to know a low limit, you'll have to know what you're testing, and then you have a high limit. That's why we define this as testing whether a value exists within a range or within a limit of two other values. So you have a lower limit. So let's say our lower limit is 10. The higher limit is 20, and we are testing 15. So does 15 fall between 10 and 20? If it does, then that means it's a true. So you put a logic 1 here, and the output is actuated accordingly. So that is how you do the limits. You must have a lower limit, you must have a higher limit, then the value you're testing. Okay, now we are writing the values in terms of numbers, just like even in timers, we were writing the preset values in numbers, maybe 5 seconds, because that's what we understand. But in the computers, it's going to be in terms of binary. Okay, it doesn't have to be in it's not written, it might be displayed as a decimal, but the computer interprets it as binary because that's its language. So for us to be able to quickly understand this, we display them in decimal numbers. Okay, but we understand that the nature of the computer is that all those numbers are compared in binary form. That is why all those registers are binary numbers. They are not decimal numbers. Okay, so again, I'm going to put this in your notes for the data manipulation instructions, both data conversion and data transfer. I'm going to send them to your CR once I complete sorting them out. And then in the next class, we'll be doing examples that combines all these instructions and see how we can solve problems that have those kind of, that requires to apply data manipulation instructions. So that's my submission to you guys today. I need to leave for a different assignment with another class. So unless there's any questions, I beg to stop here. So wacha nisikize kama kuna maswali. This is a very interesting part of PLCs, and it's very simple because most of the concepts are already familiar with you guys. All that remains is how do you apply them in different application scenarios or questions that you may receive. Do you think about them? Can you be able to invoke each of these instructions where necessary and apply them accordingly to help you solve the problem? That's what I'll be testing. So we'll do examples in the next class. Yes, Ogola.
Yes, sir. I was just asking about the mask move, whether you can recover the original source information from the mask, or there is a decryption key for the mask information.
Okay, that's a good question. You're trying to see if you're able to recover. Now, the reason the mask move is one way. It's not. If for us to be able to recover is if we were able to do a comparison backwards, so that what was the source is now the destination, and what was the destination is now the source. But because it's one way, we do not do the recovery. You cannot do the recovery. It's because you're actually, remember, when you move, you're actually overwriting. You're overwriting the contents, meaning you're replacing the contents of the destination. So we are not going to be able to do a recovery. Number two, it is a one-way operation. It's not dual operation. So we cannot go backwards and do a comparison, because if you are to recover, then now what was your destination must be compared with what was your source. So that is not allowed. So for must move, we do it one way, and because we are overwriting the contents of the destination, we cannot do the recovery. Any other question, guys, before I leave? Good. All right. So I wish you a good day ahead. I want you to, maybe because you're approaching the Easter holidays, please complete my tutorial so that as soon as we are done with Easter, I provide you, that is next week, I provide you with the CAT that you can also do. Then we can move on to something else, because I want us to move to program control instructions. There we'll spend quite some time. So, but the data manipulation instruction is quite easy to understand. So please, let's hope that by the end of next week, we can now move to the last part of our discussion, which is program control instructions. Then we can conclude it there, because PLC is so wide, we cannot cover everything. That's just not possible. We can only scratch the surface, and then you progress on your own, at least now, because you have ideas that you can work with. But we can't cover everything because it's just too wide. All right, I don't see any other hands up. Maybe, oh, sorry, let me just check if there were comments on the comment section. Okay, I also don't see any comments. All right, then let me wish you well. Hope you will be able to complete my work in good time. And so I'll see you again, I think, next week on Wednesday.